Hello everyone, welcome to Data Science Galaxy. Today we're diving into a secret weapon in data science, and that's called SVD for short, singular value decomposition. And I'm going to demonstrate right now, right here, how do we use singular value decomposition or SVD for dimensionality reduction. Let's understand what is it all about. When you think of dimensionality reduction, think of it this way. It helps simplify complex data, making model faster and often improves accuracy. Also remember, most people use another secret weapon like principal component analysis or PCA for short, but there is another powerful technique and a secret weapon that is often overlooked, and that's what is called singular value decomposition. So what is it? Singular value decomposition is a matrix factorization technique that is super efficient, especially with sparse data or highly correlated features. It is used behind the scenes in recommendation systems like, for example, Netflix and Spotify. So let's understand how does this actually work, okay? So let us see how do we do dimension reduction using singular value decomposition. So what I'm going to do next is to show you a live demo and a quick demo at that, and we'll make use of Python and we'll make use of scikit-learn library and perform singular value decomposition on a sample data set to do exactly the dimension reduction. I highly encourage every one of you to continue watching and stick around till the end. Your learning is guaranteed. Don't forget to subscribe if you're not already subscribed. Let's dive into the coding side of things, shall we? Yes, let's dive into coding. First, I'm going to import NumPy library by using the import command. Import NumPy as np. And this is one library that we would require to generate a data set. So I'm going to generate a data set that has 100 rows of data and exactly 5 features. And imagine those 5 features are highly correlated. So the idea is to use SVD on this data set of 100 rows and 5 columns or features and reduce the dimension. So let's say 2 uncorrelated features. And we will use truncate SVD functionality for it. So I need another library from scikit-learn decomposition and import truncate SVD functionality. So I will say from scikit-learn dot decomposition, right? Import truncate SVD, truncated SVD. Let's see if this line of code works. Yes, it does. So the importing of the libraries is done. So we have the NumPy for generating the data set and truncate SVD for dimension reduction. So let's go ahead and use NumPy to create this data set. How do I create a data set? I want to create a sample data set by using NumPy. So what will you do? np.random.rand, and I said 100 rows, let's just create, and 5 features of 5 columns, and the output of it, store it in an object called data. And let's see if this code works. Yes, we have the data ready. So if you want to print the data, you can see. So we will have hundreds of rows, hundreds in fact, not hundreds, sorry, 100 rows and exactly 5 columns. So the key is to imagine this data set is having 5 correlated features. So what I'm going to do is apply SVD on top of this data set to be able to do the dimension reduction. So I'm going to copy this functionality. In fact, I'm going to initialize this. Let's look at this. There is something called n components. So I could use that and then say 2 components. And let's say I'm going to capture this output in an object called SVD. Okay, so what we have done, we have basically initialized truncate SVD from scikit-learn, setting the number of components is equal to 2 to be able to reduce our data set to just 2 features or 2 dimensions. Then we'll transform the data and print out the first 5 rows of our reduced data set. So that's a dimension reduction technique using SVD that I'm talking about. Let's just execute this. Yes, it is working fine. Then I need to transform this. How do you do that? You have to use a fit transform function and pass data as the parameter. Okay, let's call another object as reduced data. You could call it with any name you want, some meaningful name. And I'm going to use SVD, that's the object instantiated in the above line of code, with the number of components being 2 for the reduced dimensions, and say dot. And there is a function called fit underscore transform, isn't it? So you will use that fit underscore transform and pass data as the parameter to this. So this would take care of reducing the number of dimensions. Okay, Let's do this. Yes, we have the reduced data. And if you print this object, you could see 100 rows intact, but the number of features, unlike the data when we printed, if you recollect, instead of 5 features, now it has the reduced dimensions. So if you want to see only few lines of code, go ahead and use index, like for example, do it like this. You will see the first 5 rows of data with only the 2 features. So what is it doing here? Basically, I have applied truncate SVD on top of the data, which is original data set of 100 rows and 5 columns that are highly correlated. And we have truncated the dimensions by specifying the parameter n underscore components is equal to 2, and reduce the dimension from 5 that was in the original data to 2 dimensions. So this is the whole idea of dimension reduction technique using singular value decomposition. Now a question may arise in your minds actually as to what is the benefit? Why did I use singular value decomposition as compared to principal component analysis, isn't it? If you pause this video, think about it and let me know in the comment section down below why I did not use PCA. I could have as well used PCA to demonstrate the same thing, but I wanted and highly encourage you to try out singular value decomposition. Pause this video and then give the comment. You know what? I'm going to reveal why I've used this. Why did I use singular value decomposition compared to PCA? Simply this. Singular value decomposition can handle sparse data, and it's particularly efficient working with matrices containing missing values. So this can be a game changer in recommendation systems or in the context of natural language processing. So next time, when you are dealing with complex high-dimensional data, try SVD. It could simplify your workflow and improve model performance. So don't forget to like, share, subscribe, and of course, that's the rigor. And you know what? I want you to try this out and let me know how did it work for you. And did you see any benefits? Take real-world setting. In a real-world setting, sparse data is what you encounter, not the data that's neat and tidy. So with a lot of missing values, and it's highly sparse data as well. So try PCA and try SVD and let me know which works best. But my personal recommendation when you're dealing with real-world setting like sparse data with the matrix, you should go for singular value decomposition over PCA. So you know what? Thanks for watching. If you made this far, congratulations. And I'll see you in the next video. Happy learning. Take care and bye-bye.